All right, so welcome. It's a great pleasure to introduce the first of our principal speakers, Daniel Litt from University of Toronto, to give us his first of four sequence of lectures, the first of which is on prehistory.
Thank you so much. It's really nice to be here. I hope this talk is as entertaining as the commencement address that you guys had here the other day. I did not prepare it while on ayahuasca, but and I probably won't mention Bitcoin, but
I have a story to tell you about that guy.
I'm looking forward to it.
I went to college with him.
Can't wait. All right, so I wanna start this talk just by talking about this first lecture will be basically on the prehistory of the subject that will be covered in the next three talks. So we'll be doing some kind of heady stuff in the next three lectures. So in this talk, I want to just connect some kind of classical problems and try to convince you that the sort of fancy technique we'll develop in the next few lectures actually can be applied to problems that people care about in the end of the 19th century and beginning of the 20th century. Okay, so what's the question that motivates us here, and also I think motivates a lot of algebraic geometry? So maybe X will be a variety. And so far I'll be kind of agnostic about what field I'm over, but think complex numbers maybe. And then you can ask, how does the topology of X, so if X is over the complex numbers, maybe it's clear what this means. There's like an associated topological space. If X is over some other field, I mean kind of invariants that have a topological flavor, like L-adic cohomology or things like that. So the question is, how does the topology of X reflect its geometry? And I think that question goes back to people like Lefschetz or Hodge or people like that. And then more recently, you can ask questions of how does it reflect its arithmetic? And by now there's kind of a standard way of formalizing this question, which is to abelianize it a little bit. So there's an abelian version of the question, which is you take your variety X, which is, let's say, smooth and proper, just so I can say rigorous things. And then you associate to it some kind of cohomology groups. And I'm going to put a little question mark decoration here because there's lots of ways you can take the cohomology of an algebraic variety. So if you're over C, you can take the singular de Rham cohomology. If you're over a more general field, you can take L-adic cohomology and crystalline cohomology and so on and so forth. Let me name my ground field K, and once one has this object, you can sort of start asking questions about how the various structures on it reflect the geometry of X, and in particular its cycle theory. So for example, if K is C and then question mark is, well, I'm going to write like Hodge cohomology, but what I mean by that is singular cohomology with the Hodge structure coming from the comparison with de Rham cohomology, then there's a Hodge structure on this group, and the Hodge conjecture, well, it tells us, or at least is supposed to tell us, how this group and that structure on it reflects the cycle theory of this variety, so, or reflects subvarieties of it in particular. So if K is a finitely generated field, and if question mark here is L-adic cohomology, well, then there's a Galois action on this group. So that's an extra structure. And then the Tate conjecture tells us how the structure is supposed to reflect the algebraic geometry of X, or like the cycle theory and so on. If K is, let's say, again, a finitely generated field, and question mark means algebraic de Rham cohomology, then maybe there's a slightly less well-known conjecture here, but the structure I think we'll talk about probably in the fourth preparatory talk and discuss it more in the fourth lecture here. There's some extra data called the conjugate filtration and the Hodge filtration. And there's again a conjecture on how this is supposed to reflect the geometry of X, which is called the Ogus conjecture. And we'll talk a little bit about that in the fourth talk. Okay, and one can keep going. You know, there's this is maybe not so obviously related to some kind of p-adic cohomology theories, which I haven't written on the board. And there's more cohomology theories where one can ask related questions. Okay, maybe I've done something that is immoral for an algebraic geometer here, which is I've asked only an absolute question, and you can also take the relative setting. So if you have x to s, let's say again is a smooth proper morphism, pi, you can associate to this again some kind of abelian invariant, which Christian discussed. So you can take the cohomology of the fibers, where lambda is some kind of coefficient object. I think the constant sheaf C if you'd like, and then there's an action of pi1 of the base on Ri pi lower star lambda on the fiber, and this is supposed to be some kind of abelian invariant of this manner. Okay. And you can ask questions about it, and again, there's lots of conjectures about what these sheaves look like, so on and so forth. Okay, so that's not what I want to talk about. What I want to talk about is non-abelian versions of all of these objects. So here, what's abelian here is like this. This group is an abelian group with some extra structure. And there's an obvious non-abelian group associated to a variety X, which is its fundamental group. And I mean this in all of its glory in various incarnations. So for example, if X is a complex variety, there's an underlying, complex analytic space, and you can take pi1 of that, but if X is over a finally generated field, you can take a tau pi1, and there are other variants of pi1 as well. So this is a very non-abelian object. Like if you're over C, it's just some sort of abstract discrete group, and it's a little too hard. So typically we slightly abelianize it, and instead of looking at this as an abstract group, we look at its representations. Okay, so this is somehow the analog of this wiggly arrow here. And part of what I want to try to convey over these 4 lectures is that any question you can ask about this has an analog here. Any conjecture you can make is an analogous conjecture here. And in fact, sometimes the logic, the philosophy flows the other way too. There's some kind of questions we know to ask about this that sort of can guide us to ask interesting questions here as well. Okay, and again, there's some relative version of this story, which is given X to S, let's say a smooth proper morphism that will soon move a little bit away from the proper setting. Well then, if you take a point in the base, there should be some exact sequence, pi1 of xs, to pi1 of the fiber, to pi1 of the total space, to pi1 of the base. And this induces some kind of analog of this monodromy representation that Christian discussed. So let me say what that is. So given this data, one gets not quite an... So what you would expect here is like pi1 of the base acts on the cohomology of the fiber, and you don't quite get that. So pi1 of the base doesn't actually act on pi1, but it has an outer action on pi1. So it has an action well defined on the conjugacy. So this maps out pi1 x s. Okay, so how does that work? Like in the topological setting, you take a loop up here and a loop down here, and you drag the loop upstairs around your loop downstairs, and you get a new loop. It's not quite well defined because that dragging might not send base points to base points. It's only well defined of the conjugacy. Okay, but what this does give you is this gives you an action of pi1 of your base on representations or isomorphism classes of representations of pi1 of the fiber. So this is really an analogy to this representation here. Okay, and so we'll study this kind of non-abelian monodromy representation too. Just to think this object is some kind of non-abelian version of monodromy. Okay. Great. Okay, so in this talk, this is all some philosophy. So for the rest of the talk, I want to talk about just the simplest possible example of all of these phenomena and how it kind of connects to the questions people were asking at the beginning of the lecture. So this talk, I'm going to take x to be p1 over the complex numbers minus some points. So this is maybe the absolute setting, and then I also want to discuss the relative setting a little bit. So I want to talk about the kind of universal family of varieties that look like this. So what am I going to do? I'm also going to take S to be the configuration space of n points, or n distinct points in CP1. So this is some algebraic variety. You take CP1 to the nth power, you delete all the loci where two of your points collide, and then you mod out by Sn. And then over this, there's a sort of universal family, which is P1S minus D universal, where what is D universal? So this is some divisor whose fiber over x1 plus xn is just the divisor x1. So this is kind of the universal family of varieties that look like this. If you'd like, you could mod out by PGL2, and I won't do that, but if you prefer like M0 and conf n, it will not affect anything that I do in the talk. Okay, so I want to talk about how some of these, what does this I don't know, category or set of representations look like, or has some extra structure too, in this example, and then what does this kind of non-abelian monodromy representation look like in the example of this family? Are there any questions before I start doing that? Okay, and you'll see soon that we get to some kind of pretty classical questions. Okay, so section 2 is just, I want to talk about P1 minus D, so that's the title of the section. So what is let's say we're over the complex numbers. So for most of this talk, I will not talk about the analogs of these objects. I'm basically only going to talk about complex pi1 and this non-abelian monodromy representation. So this talk is the analog of monodromy. And then the next 3 talks are going to be loosely organized around these 3 eras. So the next talk I'll talk about kind of the non-abelian analog of Hodge theory and the Hodge conjecture. The 3rd talk will be about the non-abelian analog of lattice cohomology and the Tate conjecture. And then the 4th talk will be about some kind of non-abelian analog of algebraic drum cohomology and this August conjecture and the questions around. Okay, so let's just go back to this kind of very basic question. Okay, so what is I'm going to write CP1 when I mean the complex manifold and P1C when I mean the algebraic variety. So what does CP1 minus n points look like? It looks like a 2-sphere minus n points. Okay, so that wasn't so hard. And so what is its fundamental group? Well, there's some obvious loops here. So to do the fundamental group, you need a base point. I use a solid dot, and then x's will be pointers. And here's some loops, which are kind of obviously not contractible. So here's a loop around my first point, and there's a loop around my last point. And maybe you can convince yourself that pi1 of this space is generated by these loops, gamma 1 through gamma n, the loops around the nth point. But there's a relation, which is that if you go around each of these loops in turn, the composite loop can be kind of contracted around the back of the sphere. So the relation to the product gamma I is the identity. Okay, so what do representations of this group look like? Well, I need to, for each of these gamma I need to pick a matrix, and then those matrices need to satisfy this identity. Okay, so let's study the question of trying to understand n-tuples of matrices whose product is the identity. It's a sort of natural object to study that you might have even wanted to study before coming up with this kind of algebra geometric philosophy that is kind of highfalutin compared to the equation gamma 1 times gamma 2 times gamma 3, etc. is the identity. Okay, so let me just write this out. So of pi 1 of CP1 minus D into, let's say, GLRC. So representations up to isomorphism is just the same as n tuples of matrices, A1 through An, whose product is the identity. Okay, what's the relation on n tuples that goes to isomorphism? It's simultaneous conjugation. Simultaneous conjugation. So I'm looking at simultaneous conjugacy classes of n tuples of matrices. So So one of these is the same as another if you can conjugate all the AIs by the same matrix to get your second tuple. Okay, this equation on its own is like not so interesting, right? Like if you fix the first to n-1 matrices here, then the last one is just determined. You can solve for it. So it's a bit more interesting if you impose some constraints. Let me do that. So I'm going to fix C1 through Cn inside of GLRC some conjugacy classes. Okay, and now we can start asking interesting questions. So what's the first question you can ask? Well, if you have an equation and some constraints, you can ask, are there any solutions? So let me call this existence. So here's the question. So does there exist A1 through AN in GLRC such that two things hold? So first of all, the product of the AIs is the identity, so it's a solution to this equation. And second of all, it satisfies the constraint that AI is in the conjugacy class Ci for all. Okay, so can you solve this equation, product of AI is the identity, subject to the constraint that the I matrix is in your ith conjugacy class? And by the way, let me just remind you, conjugacy classes in GLR are very simple. It's just matrices in Jordan normal form. So this is like a purely algebraic question that you could ask as soon as you learn what a matrix is and what Jordan normal form is, I guess. It has a pretty fancy name. It's called the Deligne-Simpson problem. So I think the reason why is that I think Deligne was the first person to ask the question in this form, and then Simpson was the first person to say something like interesting about it. And maybe if you're familiar with these people's name, it shouldn't surprise you that the answer, like the approach is really related to the fact that this problem comes from P1 minus some point. So the answer is really algebra geometric in origin. I'm not really going to say anything about the Deligne-Simpson problem unless you ask me after the talk, but let me just remark that if instead of working with the general linear group, you work with the unitary group, you really see some algebraic geometry showing up. So if you put the unitary group here, the answer, there's a sort of beautiful answer found by Agnotri and Woodward in terms of the Gromov-Witten theory of Gauss-Manians. So it's sort of maybe a little bit of a surprising connection. Okay, are there any questions about that?
So when you do this conjugate class, so do you act out this matrix simultaneously? Conjugation?
So here I just mean conjugacy classes in the general linear group. So just matrices in Jordan normal form. So each of these are subsets of the general linear group. They're just collections of matrices, not in tuples of matrices.
I see. So each matrix you individually conjugate to a Jordan normal.
That's right. Yeah. So I want to know: is there a tuple where this equation is satisfied and where each matrix individually can be conjugated into your given, it like lives in your given conjugacy class? Okay, so we've asked the existence question, so probably the next word I'm going to write down, which is uniqueness. So how do you phrase uniqueness here? Well, you can ask, so when is this solution, so this n tuple of matrices satisfying this identity, who their product is the identity, and AI and CI, well, unique, okay, it'll basically never be unique because you can always simultaneously conjugate all your matrices, unless all of the CIs are the identity. But you can ask, when is it unique up to simultaneous conjugation? So this question also has a name. So make some definition. So if so, we call A1 through AN a rigid tuple. So a rigid tuple of matrices, or a rigid representation, if you think of it as a representation of pi1 of P1 minus endpoints, or a rigid local system, if you think of it as a local system on P1 minus some points via what Christian discussed in the beginning of his talk. And Katz, so Katz completely classified these in his book, Rigid Local Systems. So maybe let me say a word about the classification because it's really cool. So how do you classify rigid local systems? Well, maybe the first observation is that when R is 1, this is really easy, right? So when R is 1, a matrix is just a number, and being in the conjugacy class, well, all the conjugacy classes are just singletons in GL1, so you're just looking for a bunch of numbers that multiply to the identity. And so what Katz did is he figured out how to reduce the general case to the case when R is 1. So what Katz found is some kind of funky operation, which is called middle convolution. And what it does is it takes a tuple in GLRC to the n and produces a new tuple, A1 prime through AN prime. This is now in GLR prime C to the n with the following properties. So first of all, if A1 through AN are rigid, then the same is true for the primes. And moreover, R prime is less than R if R is at least 2. Okay, and second of all, whatever this middle convolution operation is, and I'll tell you what it is at the end of the talk if I have time, it's invertible. Okay, so what does that tell you? It tells you that, well, you can start iterating it, and you keep decreasing the size of your matrices, right? So you go from GLR to GLR prime with R prime smaller than R, and you keep going. Well, that means R has to be 1 eventually, right? So you've reduced to the case of 1. We already classified rigid tuples of 1 by 1 matrices. And what that says is because this operation is invertible, you can generate everything by going backwards. So under this operation of middle convolution, okay, and also scaling the matrices, which I'm allotting here, everything is generated by the sort of easy to classify tuples of 1 by 1 matrices. Okay, so that's some kind of answer. Maybe let me just remark, it's like an algorithmic answer, right? Which means that if you have a question about rigid local systems or rigid tuples, it might not be that easy to answer using his classification, and in fact there's lots of open questions about rigid local systems on P1 minus some points, these rigid tuples that are still open despite there being a complete classification. That's the uniqueness question. Are there any questions about that?
So this is more like if it exists and unique, then you can do this, or without knowing the existence and uniqueness.
Yeah, so existence, somehow the classification also gives you some kind of existence criterion too, like, since they're all generated in some explicit way. So, yeah, but if someone gives you a bunch of conjugacy classes, figuring out if uniqueness is kind of easy.
When you say simultaneous conjugation, do you mean conjugating each of the AI by the same thing?
By the same thing, yeah, that's right. Any other questions?
Yeah. Does it imply like we have fewer and fewer rigid local systems as the rank goes up?
Well, I mean, there's uncountably many in rank 1 and uncountably many in every rank, so I'm not sure I understand. Yeah.
Not in the cardinality.
Yeah, I don't know how to.
You're inferring there's an injection from.
No, but it's somehow. Yeah, there's some. I'm suppressing a lot, but there's some parameter on middle convolution, and then you also do some scaling of the matrices. So it's not exactly an injection either way, and you make some choices when you execute. What really he proves is there's some algorithm using this operation to generate everything from rank 1. So I don't know if it gives you if it gives you any kind of counting statement. Yeah, I don't know if that answers it. But and what middle convolution is it gives you a bijection between components of the character varieties. So it's some invertible operation. So I don't know how to say anything more than it's invertible. Oh, okay, yeah.
I just wanted to know whether there's a natural injection.
Yeah. Any other questions? Okay. Okay. What about this relative setting? So maybe let me leave the map I'm studying on the board. So P1 minus D over D. So maybe question 3 is, well, you know, if the solution isn't unique, then there's like a space of them. And you can ask, what are symmetries? And the way I like to think of this is as kind of understanding monodromy, but it's really just some question about like the geometry of the space of solutions to this simple equation, product of AI is the identity. So what I told you is that in this setting, you have an action of pi1 of the configuration space of endpoints in CP1 on representations of pi1 of CP1 minus your endpoints. Okay, and well, this space is really explicit, right? We just said it's products of matrices that equal the identity up to the simultaneous conjugation. So let me make this action completely explicit now. So what is this action? Well, it's generated by some element sigma I, and I have to tell you what they do to an n-tuple of matrices. And what you want to do is you want to kind of flip the ith and ith plus first matrix, where the matrix multiplication is not commutative, so that wouldn't preserve this relation of the product with the identity. So instead you just fix that up. You send this tuple a1 through an to ai plus 1, ai inverse in the I spot, and the ai in the I plus first spot. Okay, so you swap ai and ai plus 1, but when you do it, you conjugate ai plus 1 by ai. Okay, and if you stare at this formula, you'll see that the product of these matrices is still the identity of these matrices, the identity. Okay, and then you get this action of the group generated by the sigma I, which is just pi1 of this configuration space, on representations of pi1 of CP1 minus, also known as n-tuples of matrices, which the identity up to simultaneous conjugation. Okay, this group has a name. It's the spherical braid group on n strands. You can look it up on Wikipedia and find a presentation. We'll never use anything except that these generate. And then you can ask questions about this. So here's some questions you can ask. Well, like, what are the dynamics of this action? So you can ask questions like, what are the invariant subvarieties? Is the action ergodic with just a natural measure here, or whatever you'd like? But maybe let me just say, like, the simplest possible question you can ask are what are the finite orbits, I think. And it turns out that this question has like a very long history, like going back to, I don't know, 1905 or something, as I'll explain soon. And it also has like a lot of significance for the rest of the talk. So I'm going to focus on this question. Are there any questions before I begin? So we have some kind of non-abelian monodromy representation, and I've asked a question about it, and I want to convince you that this question is kind of interesting and old and related to things. So we'll kind of come back to it over the course of the talk. Great. Okay, so let me tell you where this question kind of came from, and also actually where this Lin-Simpson question comes from. And I think Katz claims that this questions about rigid local system arguably go back to Riemann. They weren't thinking in terms of pi1, and pi1 wasn't invented when Riemann was working, or they were, and maybe in some sense they were thinking in this language. What they were thinking about were all of these questions in the language of ordinary differential equations. So they took all these questions and translated them through the Riemann-Hilbert correspondence that Christian explained to us. Or really, I've taken all of the questions that they were studying at ODEs and translated them through the Riemann-Hilbert correspondence to something about n-tuples of matrices. In the language from the very beginning of the talk, where I was saying that there's some kind of analog between everything we're going to talk about pi1 representations and questions about cohomology, what I just described is the Betty side of some question, and they were studying the Durham side. So so let me explain that now. So this is section 3 of the talk, which is ODE, or if you'd like, the Durham side of the story. Okay, so let me remind you, Christian introduced this category, which was modules with integrable connection on a variety with a simple normal crossings divisor. So here my variety is going to be P1, and I'm going to have some divisor D. Is this the language you used, Christian, for regular singularities? So there was no extra reg or something?
Not per reg when you restrict that.
Okay, good, excellent, because that's also what I have used in my notes. So. Okay, so this is modules with integrable connection on some pairs, so let me remind you what this means. So this is pairs E nabla, where nabla is a C-linear map from E to E tensor omega 1. Here, this is P1 log D. So I think I complained when Christian said that this was one forms with poles along D. For curves, it is one forms with poles along D. So this is just the same as omega 1 twisted by D. You can ignore the log. So for curves, it's the same. So let me remind you, this is flat bundles on P1 with regular singularities along D. That's terminology. Okay, so what is this really? It's a bundle and a rule for differentiating sections to it along vector fields that vanish at D. That's how you should think of this. Great. Okay, so maybe let me give you an example. So these things are supposed to correspond in some way to local systems on P1 minus D. In fact, there's many of them for each local system on P1 minus D. But they all restrict to the same thing on P1 minus D. So there's many possible ways to extend. Okay, but here's an example. If I take, let's suppose I take, let me assume infinity is not in D just for convenience. I'm going to take B1 through Bn, which are matrices with complex coefficients, R by R matrices with complex coefficients. And I'm going to assume that the sum of the Bi are 0. So this is morally like the log of the equation product is 0. It's not literally that, but it's sort of related. And then here's a flat vector bundle with regular singularities. I'm going to take OP1 to the R, and I'll take the connection, which is the exterior derivative, plus sum of Bi over Z minus Xi. Xi are my points of D, DC. So this is something with simple poles at the xi, and this condition tells you there's no pole at infinity. Okay, so this is what's called a Fuchsian ODE. So in my comment at the end of Christian's talk, that I think maybe this is what Hilbert's 21st problem was really about. So Fuchsian means that this bundle is trivial as opposed to being like, having some, like being O to the R plus O of 1 or something like that. Okay, okay, so this is some kind of ODE, so maybe let me make a remark. So Christian explained that these ODEs are related to local systems on P1 minus D, and I think at the very end he sort of told us how to understand what happens on a punctured disk. And so here we have like an n-tuple of matrices, and how is it related to these matrices Bi? And the point is that Aj is conjugate to x of 2 pi I B. So at least knowing the conjugacy classes of these Bi's tells us the conjugacy classes of the A's. So if you look at the local system corresponding to this flat bundle. Okay, just a warning is that like it's actually very hard to compute the monodromy of this flat bundle. You don't just exponentiate all these Bi's and then say you're done. Like you have to do some kind of funny integration to figure it out. So like if someone gives you these Bi's, producing the AI's, and not just their conjugacy classes, is much more challenging. Are there any questions about this? Okay, so now you can ask questions. You can ask like, given some conjugacy classes in here, can you find matrices with this property? So that's like the additive version of the Deligne-Simpson problem, and it's related to the old Deligne-Simpson problem in a sort of subtle way. You can ask, when is the solution to this equation unique? So that's some analog of this question of rigid local systems. And then, okay, so what I want to explain is the analog of this monodromy behavior. Okay. And so this is the non-abelian version of the Riemann-Hilbert correspondence. Okay, so here's the question you can ask, which is the analog of the monodromy, which is the monodromy of pi1 s on representations. So as you vary the xi, so as you move these points around in the configuration space, how to change the bi so that the monodromy representation stays the same. What do I mean by that? Well, moving these xi's, so deforming this divisor d doesn't change the homotopy type of P1 minus d. It's still a sphere minus n points. So if you move the xi a little bit, it makes sense to ask, well, like, let's say if you keep the bi the same, it makes sense, how did the monodromy representation change? There's no reason it should stay the same. And in fact, in general, if you don't change the bi's, the monodromy representation will change if you start moving the xi's around. Okay. So let me tell you the answer. And this is something that has been known for a really long time. This is due to Schlesinger in 1912. So the answer is that as you move the xi's, to keep the monodromy the same, the bi's have to satisfy some differential equation. And let me just write it down, because it's cool. So it's, you take dbi dxj, so when I is not equal to j, you say this should be the commutator of bi with bj over xi minus xj. So that's some nonlinear ordinary differential equation these things have to satisfy. I have to tell you what to do when I equals j. And what you do is you just make sure that this equation stays true. So you say that the sum over I of dbi of dxj is 0. So you can solve for dbi dxi by plugging in these terms for all of them here. So let me say a little bit about how this ODE is like related to this monodromy action. Right. So what you want to do to understand this action here is you want to take a representation of pi 1 and then drag d around in some path in the configuration space. That representation corresponds to an ODE, and now what you can do is you can analytically continue the bi's as you drag the xi around through configuration space. And that analytic continuation is solving this ODE. So this ODE captures exactly the same data as this monodromy representation. So I'll discuss this more in the next talk, but this is a non-abelian version of the Gauss-Manin connection in this example. And maybe let me just remark, so Schlesinger wasn't the first person to try to write this down. So I think Fuchs in 1905 did the case where you have 4 points and all the bi's live in SL2, they're traceless 2x2 matrices. And in this case, this equation is called the Painleve VI equation. So this is why I'm calling this prehistory. This is sort of where all these questions come from. Right. If you go on Wikipedia and look up the Painleve VI equation, you'll find something that's much nastier than this, but it's the same, up to some kind of complicated change of variables. Yeah.
What's the summation index?
So you're summing over I. So I equals 1 to n. Does that make sense?
Yeah, you have all I of the.
Yeah. So all j. Sorry, there's one of these for each j. Yeah. Thank you. Yeah. Great. Okay. So what does this have to do with this dynamics questions here? So for example, I asked, like, what are the finite orbits of this action? So that has an interpretation in terms of this differential equation. Well, what does it mean to have finite orbit under pi 1 of this configuration space? It means that when you start analytically continuing your solution to this ODE, it has finitely many branches. And if you unwind that a little bit, and what I'm saying is not totally obvious, it's not so hard. So finite pi 1 conv n orbits on representations of pi 1 of CP1 minus d are the same as algebraic solutions to the Schlesinger equation. Okay, and this is something people have been interested in for a long time, and I think the first example I found of someone trying to classify algebraic solutions to this ODE is some paper of Garnier from the 1920s. Maybe let me just say a few words about the history just in this special case, which is like this case which has had the most work. So in 1895, which is, well, Painleve had discovered some kind of special cases of this equation, and he claimed that the solutions were new transcendental functions. And he was working in 1895, so I think his arguments were not rigorous by modern standards. And then there was a huge amount of work over, well, until about 2014, trying to make it precise by Umemura and other people. And their precisification of his claim relied on classifying algebraic solutions in this case. So maybe let me say a word about the classification of algebraic solutions. So that's the same as classifying these finite orbits. Just when you have, so this is when you have 4 points. So D is, I've been using N to denote the size of D, and R is 2, so I have 4 2x2 matrices. Maybe before I say the classification, let me just point out this is like a really concrete problem. Like you have 4 2x2 matrices, you start fiddling around with them in this way, and you want to know which 4 tuples have finite orbit up to simultaneous conjugation. So that's like something you could explain to a high school student. Okay, so I think, I mean, this goes back to Fuchs, who I think wrote down the first algebraic solutions, but I think it's really picked up with work of Hitchin, who actually discovered the same algebraic solutions Fuchs did in 1905. And then the first real attempt at some kind of classification was Dubrovin and Matsako, who studied the case where 3 of the conjugacy classes were 1, 1, 0, 1, and the 4th was diagonalizable. And if you look at they have this amazing Inventiones paper where they write down some 10-page algebraic solution to this ODE. It's really crazy. And then there was a huge amount of work done by Bolch, Kitaev, and other people who I won't list. And then the classification was finished by Lissovi-Tiki in 2014. And what it looks like is that there's 4 continuous families of algebraic solutions or finite orbits. There's 1 countable infinite family, and then there's 45 exceptional finite orbits or algebraic solutions. So the nature of their classification is, so first of all, they didn't find any new examples. What they showed is that the list of examples other people had found was complete. The proof was computer aided. So as far as I know, there's no fully human readable proof of this classification yet, although I'll say a word about that. And it relies on some arithmetic, so it relies on some effective version of the Manin-Mumford theorem, Manin-Mumford conjecture for tori. And I won't say anything more about this. That's what, this cool math here is what I'm saying. Okay. Are there any questions about this? Yeah.
How hard is it to see the correspondence theory between the finite orbits and
Yeah, it's not that hard. So somehow the point is that if you drop the word finite, it's still true. Like there's an equivalence between orbits and solutions, right? So I sort of explained that. Like the point is that how do you go from how do you go from orbit to a solution? Well, you start with some representation of pi 1, and you start analytically continuing the corresponding local system as you vary the x values, and then the branches of that analytic function exhaust the pi 1 confine orbit. Yeah. So really, the content is saying that a finitely branching solution is algebraic, and that's some kind of non-abelian version of this Riemann-Hilbert correspondence that Christian described. Great. Okay, are there any other questions about this? So this is some question about 4 2x2 matrices, and the answer is pretty crazy.
So if n is just 3, is the same R equals 2?
Yeah, so if n is 3, it's not interesting, and the reason why is it turns out that basically all the local systems are original. So another way of saying that is that this group, sigma 1, sigma 2, actually ends up the action factors through S3. So all the orbits are finite. Maybe it's worth remarking, somehow why is this finite orbit question interesting? Like one reason is that it actually generalizes this question of classifying rigid tuples. The point being that any rigid tuple automatically has finite orbit. So why is that? Like a rigid tuple is determined by the conjugacy classes, and this action just permutes the conjugacy classes. So the action on any rigid tuple will factor through Sn. And so what I said when n is 3 is just that all the tuples are rigid, which means the action factors through S3. Does that make sense?
And does countably exceptional families are already
So these are actually not rigid local systems. They're rigid as finite orbits, if you will. So if you look at the space, the group action on the finite orbits, they're rigid in the sense that they don't deform as finite orbits, but they're not rigid as local systems on dual lines. Any other questions?
So by algebraic solution, do you mean like a P is like a n by n matrix consisting of meromorphic functions?
Or algebraic functions. So
So
you mean,
one is a meromorphic. You think
so they can be multi-valued.
yeah.
Yeah.
And by talking the algebraic, do you mean there could be like an essential similarity or something?
Yeah, or infinite branching. Yeah. So if you drop the word finite, then you just get holomorphic solutions. But yeah, so algebraic solutions just means that these BIs are matrix valued functions, and the entries of those matrices are algebraic over the field CZ. They satisfy a polynomial over CZ. Yeah.
So I have a question, but I don't really have the correct formula yet.
That's okay.
So this cluster thing is related to the non-abelian Gauss-Manin connection.
Yeah.
I've read some conjecture of Simpson's that's like relating the Gauss-Manin connection to rigid local systems. Is that like relevant to this?
Morally, at least, it's in some sense the topic of part of my third lecture. Yeah. Maybe let me just say a word about that, and then I'll continue past this example, which is like, so what is the Gauss-Manin connection? So Christian explained that if you have a family of varieties, you can take their cohomology, and you get a ODE associated to it. So a bundle with flat connection, and that flat connection is called the Gauss-Manin connection. So here I took some kind of non-abelian cohomology, which is the space of representations, and I associated an ODE to it. So that's why this is the non-abelian Gauss-Manin connection. And when I say I associated an ODE, I mean Schlesinger associated an ODE. And by the way, I mean this is easy. This is like seeing that this is the ODE that controls how you deform these things while keeping the monodromy the same is not a hard problem. We can discuss it in the break if you'd like, or for lunch, but you should try it yourself. You can do it. It's a few lines. Okay, so let me say a little bit about what happens when n is bigger than 4. Let me go over here. The short answer is we really don't know. I mean, as you can see, the n equals 4 case kind of took, I think I said like 110 years, so 1905 to 2014. But I know how to say a little bit, and so the reason I want to mention this is because it's some kind of application of like the fancy like non-abelian Hodge theory, rigid local system stuff that I'll talk about in the next few lectures to a question about 2x2 matrices. So I just want to try to convince you that some of this stuff is like relevant to a question that you might have cared about when you were a freshman in college or something like that. Okay, so here's the question. So can we classify finite orbits, so finite pi1 on n, CP1 orbits on, let's say, two-dimensional representations of pi1 of CP1 minus n points? Okay, and the answer is almost. So I just want to kind of state the classification, and then it will kind of hopefully explain to you that there's some kind of fundamental something fundamental about these finite orbits. Like the way we can classify them is by relating them to something else. So maybe let me make a definition. So here, are there any questions about what the goal is? And let me just remind you, I mean, it's really, I wrote pi1 of content there. Really, I'm just asking about n tuples of 2x2 matrices, where when you start doing these operations, you always get that where you start. It's not supposed to be a complicated question. Okay, so here's the definition, which will help me state the theorem. So A1 through AN in SL2 to the n is interesting. Okay, and the point of this definition is that I'm just trying to rule out the cases which are easy to classify. So there will be a bunch of cases which are sort of well understood, and then I'm going to say something about what's left over. Okay, so first of all, one, it has finite I1 conven orbit. So it's something we're trying to classify. So two, it generates a Zariski dense subgroup of SL2. This is just because it's easy if it doesn't somehow. I mean, when I say easy, I don't mean like I don't mean trivial, I just mean someone else has done it. So for example, in the case where the matrices are upper triangular, it's like a pretty deep work of Cousin and Moussard and equivalent, like McMullen did more or less the same thing. Okay, three, no AI is plus or minus the identity. So this is just, it's sort of stupid. If one of them is the identity, you just throw it away. If it's minus the identity, you multiply it by -1 and multiply one of the other matrices by -1. Not very interesting. Okay, and then four, so the interesting part is related to your question. So it doesn't move in a continuous family of finite orbits. Okay. So what do I mean by this? I mean, being finite orbit means you're fixed by some finite index subgroup of this group, and I want the corresponding fixed point to not be in a positive dimensional space of representations, also fixed. Okay, so it's not, shouldn't at all be obvious that 4 is like ruling out some easy condition, and that's because I'll explain where it comes from next time. So there's very deep work of Corlett-Simpson, which I'll try to give you an idea of next time, which lets you kind of classify the continuous families. And so in this example, the actual classification was worked out by Iara in 2013. Okay, so let me now tell you a theorem. How much more time do I have?
You can take until, I mean, he started about 5 minutes.
Okay.
So I would go for 5 minutes.
Sounds good. Oh, perfect. Okay, that's exactly, I'm right on time. Okay, so let me tell you a theorem now. So this is joint with Josh Lamb, Aaron Landsman, and I guess myself. And so maybe let me just say like the sort of content here is really coming from this work of Corlett-Simpson, non-abelian Hodge theory, and also work of Katz, as you'll see soon. So suppose A1 through AN is interesting. So that's the thing I just defined. This is the annoying part, some AI has infinite order. Okay, so I'm going to give you a complete classification as long as one of your matrices is infinite order. What's left over? It's the case where all the AIs have finite order, and that we don't know how to do. So what's the classification? There exists some explicit complex numbers, A1, alpha 1 through alpha n, and lambda, and C star, such that alpha 1 A1, alpha n AN, so if I scale these matrices by some numbers, they have the following form. I'm going to write them in MC lambda of B1 through Bn. Okay, now I have to define some terms. So first of all, where B1 through Bn are unfortunately not the same B's from before, they're now n-2 by n-2 matrices. So that's typically a big matrices. If n is not 4, I've made my matrices bigger. And they generate a finite complex reflection group. I'll say what this means and why it's a classification. Okay, so first of all, what is this MC? So this is Katz's middle convolution operation. From the beginning of the talk, I'll say a word about what it actually is in a second. But first I want to tell you what is a finite complex reflection group and why is this actually a classification. Okay, so Okay, so what is, maybe let me make a definition. So A, let me call it B in GL RC is a pseudo-reflection if two things happen. First of all, B has finite order. And two, the rank of B minus the identity is 1. Okay, so what does this mean? It means B fixes a hyperplane and has finite order. So if it's a reflection and has order 2 and fixes a hyperplane, this is just some generalization of a reflection, where you say it doesn't have order 2 anymore. Okay, and then the definition is an FCRG, finite complex reflection group, is a finite subgroup of GLRC generated by pseudo-reflections. Okay, so that tells you what a finite complex reflection group is. Before I say a word about what middle convolution is, why is this a classification, right? So I've taken my 2x2 matrices I'm kind of interested in, I've related them to my system n minus 2 by n minus 2 matrices, and I know something about them. They generate a finite complex reflection group, but they're big matrices, like what does that give you? So the point is that these have been completely classified. So these were classified in 1954, I think, by Shepard and Todd. And there's one infinite family of them and 34 exceptional ones. So the infinite family is easy. You take permutation matrices, and instead of ones, you put roots of unity. More or less it. The 34 exceptional ones, most of them you've heard of. They're like the Weyl group of EH, or the automorphism group of the icosahedron, and that kind of thing, but there's a few that you haven't heard of. Okay, so this is really a classification. Like it's just, we've reduced it to some other classification that's been known in the literature for a long time. The sort of key input is that this whole problem is a Hodge theoretic interpretation, which I'll say something about in a minute. But maybe my last minute. But maybe let me just remark that there's a very simple corollary. Suppose A1 to AN is interesting. Some AI has infinite order. Then n is less than or equal to 6. And the proof is you use the classification and then just go through all the finite complex reflection groups. I'd be very interested in a simpler proof of this. Okay, so now let me kind of say, of course I'll kind of describe some of the ingredients of the proof. I mean, I will not actually return to the proof in the next 3 talks. This is just meant to be some motivation to tell you that this is related to simple things. But the upshot is that whatever this middle convolution does, when you apply it to a finite group, it produces for you a family of curves. So MC lambda of V1 through Vn, this is some representation. It appears inside of R1 pi lower star C, where here pi from, let's say, y to P1 minus x1 through xn is an explicit family of curves. Okay. So what we really show, an explicit family of curves constructed from this finite complex reflection. So what we really show is that these finite orbits are related to algebraic geometry. It's a Hodge theoretic interpretation of this finite orbit condition that lets one understand the algebraic geometry behind them. And so that's sort of what I want to stress. So for the next 3 talks, we'll be talking about local systems and representations of fundamental groups of algebraic varieties in general, but we'll see that the ones which kind of show up in cohomology, the ones which come from algebraic geometries, play some special role analogous to like cycloclasses in topology. And so we'll return to that notion of coming from geometry and rigidity and moving in a family and so on again and again throughout this. All right, that's what I wanted to say.
Do these other finite order orbits that you maybe aren't interesting, do they also come from geometry?
Yeah, so what ends up being true when it is that, so let me say a couple words about this. So first of all, I switched from GL2 to SL2. That's not a real condition because you can just, if you have something in GL2, you just multiply it by like the square root of 1 over the determinant to put it in SL2. Okay, so from geometry, it means that you have to be either Zariski dense or have finite image, so that there's some little restriction there. So for example, the upper triangular ones can't really come from geometry. They have some other geometric interpretation, which if you look in McMullen's paper, Great Groups in Hodge theory, it's sort of implicitly there. But yeah, if you look at the ones with finite image come from geometry, but if you look at the Zariski dense one, it's actually a consequence of this theorem of Corlett-Simpson that as long as all the AIs have only roots of unity as eigenvalues, they have to come from geometry. That's not totally obvious from Corlett-Simpson, but it's like Corlett-Simpson plus epsilon or something. So they do, and somehow the point is like, well, what are you really trying to do here? You're really, in my view, like one of the main goals of algebraic geometry, like understanding the topology of algebraic maps boils down to classifying local systems that come from geometry, and that's what I really view this theorem as doing, sort of classifying local systems which come from geometry on P1 minus some points, or P1 minus generic points, basically. So the answer is yes, so they all do come from geometry for some almost formal reasons, with this sort of root of unity eigenvalue condition, but that doesn't mean you can write them down, right? Thank you. Yeah.
Instead, you wanted to look at representations of the fundamental group of some other projective curve minus some number of points. Could you make as much note about that?
Yeah, so I'll talk about that a little bit in the next talk, but yeah, so yeah, let me say, that's a great question. So let me say one of my favorite questions in all of algebraic geometry, or you can also think of it as a question in pure group theory or topology, which is, so let's suppose sigma Gn is, well, what is it? So genus G surface minus n points, right? You can look at representations of pi1 sigma Gn. So maybe this is what you were interested in. And then there's some kind of non-abelian monodromy action on it. Well, what's the action by pi1 of mg? And pi1 of the moduli space of genus G curves with n punctures. If you'd like, this has a pure topological interpretation. You take the space of orientation preserving homeomorphisms of sigma Gn. So this is some infinite dimensional topological group. You take its component group, exactly the same thing, up to finite index. That's a wiggly arrow means finite index. And you can ask, what are the finite orbits? Aaron Lansman and I do have a theorem on this, which I'll say next time if people are interested in. I probably won't have time to say anything about the proof. So we understand the answer when G is big compared to the rank. When G is not big compared to the rank, it's very interesting and very open. And I think somehow these finite orbits have actually they're kind of important. I think they maybe I can say why I think they're important after the talk. But yeah, so it's a very interesting question. Is that? Go ahead. Any other questions?
I have maybe more details. So because that you have this CP1 thing, and I can be thinking if you replace CP1 by just CP1 minus 1 point, which is just C, then it seems like you get simpler, right? Because you just get a break group, the usual break group in the pi1, and then the matrix, the other side you just get a bunch of matrices without any condition at all. So is this a similar picture, or is it a
it's sort of this? I would say it's the same picture. Somehow this map from the braid group to the pure spherical braid group, and the kernel is Z, and the action will factor through that map. So it'll be literally the same picture somehow. When you study these dynamics, the conjugacy classes don't intervene in any way, right? So somehow the fact that you've ignored the point at infinity or whatever just means you've added a point. You've added infinity as a new point to your divisor. Yeah, I think there's just no difference.
So is there a reason why one of the picture is it's more easier to work with because
I think they're just the same picture somehow. So I read it this way because I think it's useful to have a compactification in mind if you think about these regular singularities, which Christian discussed, and somehow, of course, I didn't say anything about proofs, but all the proofs go through that equivalence and then use somehow ODEs on the moduli space curves and that kind of thing. So you need a compactification floating around always. So maybe that's why
always work with CP1 rather than A1.
How many samples I just want to make sure. So, connection between like the problem of like matrices or function classes and this monodromy is if you have a monodromy, then you can get a different solution. Is that right?
Yeah. So this non-abelian monodromy business was right. So you have one solution to this equation, product of AI is the identity, right? And then I made a new one. It's like AI plus 1, AI inverse AI. Yeah, so given one of these n tuples of matrices, you get a new one. And it turns out, I mean, I just told you the formula, but it turns out that this is exactly how pi1 of the configuration space acts on the solution. So I don't know if that answers your question.
I was gonna ask, so if you have a non-unique solution, is it always conjugated with monodromy?
It's always conjugate.
Like if you have something that's not rigid, like you have two different things, it's not unique, is there always a monodromy that goes with? Like, is this monodromy detecting exact? Like,
oh, I see. Yeah, so no, I mean, somehow the point is that there's many non-rigid tuples which still have finite orbit under this action. So even if the space of solutions with fixed conjugacy classes is positive dimensional, so typically the action on it will be kind of big, like a random point will be moved around a lot, but there might be some special points that are fixed by them. I don't know if that is what you're asking.
Oh, I just want to ask, like, is the question completely translated into the monodromy question? Like, the original question was matrices, can you completely translate it into monodromy?
So when you say the original question was matrices, you
like
mean,
this, like you have A1 to AN with some conscious classes, like classified
oh, so you mean the original existence question?
existence in you.
No.
Not the existence. I mean, like, how big is the uniqueness?
Yeah. So what I think so. The uniqueness question is about you can look at the set of tuples with multiplied identity at the simultaneous conjugation in certain conjugacy classes.
Yeah.
So that's some algebraic variety. Uniqueness is when is that a point? And what's true is that when it's a point, it will always have finite orbit. But
okay, but it's not a.
But it's it's classifying finite orbits is more general. So there are some finite orbits that don't correspond to those. I think that's sort of why it's an interesting question.
All right, let's thank Daniel again.
Yeah, I'll talk about it.